here I'm going to show you how to gather the data that you're going to need for Lab 6, Newton's second law. So this lab is a little different in that it's kind of a virtual lab, or kind of a simulation, because you're not actually going to be getting out lab equipment, you're going to be gathering data from a video. So first you need to open up the video, so click that link here. And what we have is a cart on a track, on a low friction or a negligible friction track. And there's a fan here that will blow the cart and accelerate it down the track. And so this video here, we can pause it, or we can start it, we can pause it, we can advance frame by frame, and then I'm going to show you how we can use some of the other features of the video to actually get data and measurements. So the first thing we need to do is go down here to Fan Force and choose Fan Force 1. And this will load the video where the fan is blowing the weakest. And there's 4 different videos here. Fan Force 2, it blows a little harder, 3 harder than that, and then Fan Force 4 is the fan blowing, the video with the fan blowing the hardest, and so it provides the greatest amount of force on the rest of the cart. So I'm going to load up Fan Force 1, and what we need to do here is also go back and make sure that you've got your data table written out. So make sure that you have your data table here so that you can actually start writing down the data as I show you how to get it. So we've got the 4 different videos here, video 1, 2, 3, and 4, and then here's where we're going to record the actual number of newtons that the fan provides in each video. And then later I'm going to show you how to calculate the acceleration provided by that fan. So first we need to load up Fan Force 1 video and get the actual value for the force provided by the fan. So first I need to, Fan Force 1, and this is important, you need to make sure the frame rate is the 240 frames per second, so the slow motion. So I'm going to start the video, and notice it's in slow motion here. And down here at the bottom is how I'm going to get the force provided for the fan. So what I have to do is wait for his hand to come off the cart and for it to be still. And so the fan is blowing here, but the spring is keeping it from moving. And so to get my fan force, I go down here to where it's zoomed in on the spring. I find the front edge of the spring, and I read off the number of newtons. So this line right here is 0.1 newtons, but the spring is at one line before that. So this is going to be 0.09 newtons, because if I count up, I go 0.01, 0.02, 0.3, 0.4. Here's halfway, so 0.05, 0.6, 0.7, 0.8, 0.09 newtons. Not 0.9 newtons, but 0.09 newtons. So go over here and fill in your data table 0.09 newtons. Next we need to, let's just go ahead and watch the video and just see what happens before we talk about how to calculate the acceleration. So the person here is going to cut the string, releasing the spring, and then the fan will accelerate across the track. So it starts out moving very slow, and slowly but surely it picks up speed and starts and it is accelerating across the track. So one thing I want you to take notice of is there's a little yellow light right here, and this is going to be important because in just a moment the yellow light is going to go off, and what that signifies is that the fan is going to stop blowing. The propellers will keep spinning because they need time to wind down, but the force of the fan goes to 0 when that light turns off. And so if we keep playing the video, watch this yellow light, eventually it's going to turn off right about here. Okay, so let me back it up a few frames and get the exact frame. So at 7:55, the light is on, and right here, the light is off. So right here at frame 7:57, the fan has turned off, and it is no longer providing any force on the cart. And so the cart now is going to move with a constant velocity. And so you'll see that the blades are still spinning, but the blades are just winding down. They're not actually being powered by anything. So the goal, again, was to calculate the acceleration of the cart. So I'm going to back the video up, and what we're going to do is we're going to do an annotated velocity graph and use that to start filling in all the numbers and stuff, and use that to calculate the acceleration of the cart while the fan is on. So over here, make my velocity clock reading graph. And so I'm going to start the graph right when the cart is at rest before the spring is cut. And so right about here, give or take. And so until the string is cut, the velocity is 0. It's not moving. So I'm going to go over here, and I need to represent that part of the motion on my velocity graph. Okay. So now what I'm going to do, because I need to make sure that I mark this clock reading here. So I need to figure out what that clock reading is. So let me make a single line there. Single line at 0. There we go. Once more with feeling. Additionally, make sure that you're following along with me. If you have not started drawing this graph with me, go ahead and pause the video and get that set up. So what I want to do is find the clock reading from when the string is cut. So let's find out where the string is cut, can back it up and see right about here. I can see that the string right there's that break in the string. Okay, so now getting the clock reading here is a little, it requires a little math, but we'll get it. So the frames here, that's 296. So that means 296 frames have passed. Now, that's not the number of seconds. To figure out the number of seconds, we have to do 296 divided by the frame rate. So what this is saying is that there are 240 frames in a second, and so there have been 296. So I should get something a little more than 1 second. So if I do 296 divided by 240, plug this into my calculator, I get 1.233. So I'm going to go back over here, and I'm going to call this T1 is equal to 1.23 seconds. Okay. So now I go back over here, and the next thing I need to do is find out the clock reading when the light turns off. And so here the light is on, so the fan is blowing and accelerating the cart. So during this time, the cart is speeding up. Go over here, let the video play. It's going, it's going. Oh, it's turned off. Let me back up to the exact frame where it turns off. And if I go here, 7:56. Okay, so there's the light is off, frame 7:56. And then to get my clock reading, I have to do 756 divided by, so 756 here, divided by 240. And if you do that in the calculator, you get 3.15. So go over here, drop my dashed line, and then I'm going to call that T2 is equal to 3.15 seconds. Okay? And now after the fan is off, the cart travels at a constant velocity for the rest of its time. So I need to show that right here. Okay, let me make a little more room on my graph. And so the last thing I need to get is the amount of time that the cart traveled at that constant velocity. So I need my T3. Let me set it up over here. Okay. So to get this, I'm going to go back to the video, and what I need is the time that it takes for the cart to travel 30 centimeters, because I need this measurement here. So what I'm going to do is I'm going to find out where the 0 mark is, okay, right here, and look down at the cart. And if I notice, the back of this gray thing here is lined up with 0 centimeters. So I need to advance the video to where the back of this little gray thing here is lined up with 30 centimeters. Okay, so take the video forward, almost there, and so right here, 30 centimeters is lined up right with the back of the cart. And I see over here, that's frame 889, and so to convert that to seconds, I do 889 divided by the frame rate, which is 240. And so I get 3.704. So I go back over here, 3.704 seconds. Okay. So I've got all my times, but I'm not quite done with the velocity graph yet. Next I need to put this 30 centimeters in here because I'm going to need this to calculate the velocity of the fan, or of the velocity of the cart, which I can then use to get the acceleration. So the 30 centimeters here is the distance traveled while the cart was moving at a constant velocity. So I'm going to go find the part of the velocity graph that is constant velocity, which is this rectangle here, and I'm going to call that delta x. And I'm not going to do this in centimeters, so eventually this needs to be converted to meters. So I'm going to do 0.3 meters, because 30 centimeters is equal to 0.3 meters. Okay? So we're saying that in those, between clock reading of 3.15 and 3.704, the cart traveled 0.3 meters or 30 centimeters. Okay? And to finish up this annotation, I need to get the final velocity, which I don't know what it is yet, but I'm going to go ahead and mark it here with VF. Now the advantage is that the velocity here at this point, because it's constant, is the same as the velocity here. Okay, and so these numbers, I'm going to use the same variable because they're the same velocity. And so if I had the velocity here, I could use that to calculate the acceleration, because I know down here that VI is 0. So to get this velocity, I have to use the area of my graph, of the velocity graph. So let's make some room over here. Scooch over. Now, I know that the area of a velocity graph is equal to delta x. And so if I look over here, this is a rectangle. And so that means that my area is going to be base times height. Okay. So now if I look over here, I know what delta x is. That's my 0.3 meters. So I'm going to substitute in 0.3 meters for delta x. Now the base is this distance here in purple. Okay. Now the tricky part here is that this gap here, this time interval, is not 3.704. What I need is the interval between 3.15 and 3.704. So if I subtract these values, so if I do 3.704 minus 3.15, I get, plug that into my calculator, minus 3.15, I get 0.554 seconds. So over here, 554 seconds is my base. And now the height is this in red right here. I don't know what that is. So I'm going to use the variable for that height, which is VF. So I go over here and I write VF. Oops. Scooch this over. Okay. So now I've got an algebra problem. Okay, you can see it a little better. So I've got 0.3 is equal to 0.554 times VF. So to get VF by itself, what I'm going to do is divide both sides by the 0.554. So 554 seconds, that cancels out. And so I get that VF, get that VF is equal to 0.3 divided by 0.554. And when I plug that into the calculator, I get, let's try that again, 0.3 divided by 0.554. I get 0.542 meters per second. Okay, so I'm going to go up here and, what did I say, 0.542. So I'm going to go over here, put this on my graph, and so that's 0.542 meters per second. Okay, now we're almost done because I need to use this information to get the acceleration. And so the acceleration is going to tell me the number, the meters per second of the velocity going from 0 to 0.542. So I'm going to go down here and make some room, and we're going to do an acceleration graph. Okay, so go here. I know the acceleration is going to be constant. Okay, now I want to make our graphs line up here. Here we go. So I'm going to bring these dashed lines down from the velocity graph because they're going to be useful, because the velocity graph is going to have 3 sections, so this one needs to have 3 sections as well. So there's acceleration, clock reading. And so during the first part of the motion, I need to have one more here. Okay. During the first part of the motion, the cart was not moving at all, so the acceleration here was 0. And then if we look up here, while the cart was accelerating, while the fan was on, we have a positive acceleration, and that's the number we're actually looking for. Okay. And then after the fan was off, after the fan was off, the velocity was constant again, and so the acceleration jumps back down to 0. Okay. So to give this variable names, here's my A. I already know T1 and T2, so T1 is 1.23 seconds. T2 was 3.15. Okay, and now we need to represent the area of this. That's our change in velocity. So we've got delta V. Now here, I can't calculate the area because I don't know the height of my rectangle here, but I can figure out the change in velocity, and that one's kind of easy. The velocity goes from 0 to 0.542, so that's a change of 0.542. So my change in velocity here is 0.542. And so that, again, is the area of this rectangle. Okay. So the goal, the whole point of this was to get the acceleration. Okay. So I'm going to use the area of a velocity graph to help figure that out. So the area of a velocity graph gives you delta V, and so this is also a rectangle, so it'll be nice and easy. So I know that that means the area here is going to be base times height, because it is a rectangle. Now I can start plugging in my numbers. I see over here delta V is 0.542 meters per second. My base is this line here in blue, but like last time, it's not 3.15, it's the gap in between 3.15 and 1.23. So I need to do 3.15 minus 1.23, and I get 1.92. Okay, that's my base. Okay. My height is the acceleration. I don't know what that number is, so I'm going to leave it as my variable a. Okay. And like before, I've got a simple algebra problem. We've got 0.542 equals 1.92 times a. So to get rid of the 1.92 and get a by itself, I'm going to divide both sides by 1.92. And so I get a is equal to 0.542 divided by 1.92. So I'm going to do that in the calculator. I get 0.282. So I get 0.282 meters per second Okay, and this was the calculation I was trying to make all along. So I go back to my data table, I put 0.282 into the acceleration, and then move on to the next video. And so this process here is going to be the same for each one. The fan starts out not moving. You have to sketch and annotate your velocity graphs to make sure you get the stopping part here at the beginning, get the 3 different clock readings, and all of that. The one thing you need to watch out for, so if you go to fan force 2, the thing you need to keep an eye on is that over here when the light, let's refresh and try again. So fan force 2, let it play this time. Remember to go to 240 FPS. And hit play. I'm not sure what's going on here. Let me pause the video and see what I can figure out. Okay, here we go, figured it out. So what I was saying is that the thing you need to watch out for in the later videos is that the light doesn't turn off at the exact same moment. So this is fan force 2, and we'll see here that, and there it goes. In fan force 2, the light turns off in a different spot. So you'll notice here that the 0 centimeter mark is lined up with about halfway on this block, and not on this little gray part here, and not the back of it like it was in the first video. And if I go over here to fan force 4, it may line up in a different spot as well. So if I go over here, notice that when the light turns off, the 0 centimeter mark is lined up with about halfway down the cart, whereas in the first video 0 centimeters was right here. So you have to be a little careful about that. Once you do all 4 fan forces and you calculate the accelerations, you need to go on and do your graph and do all of the sections of the data analysis on page 2 of your notebook. If you get confused on how to calculate the acceleration of the cart, that's really the difficult part here. Go back to the earlier parts of the video and watch it. That's all.